Another problem in the category of exact solutions is now we consider the very famous problem, what we know as Stokes flow. The famous mathematician who has contributed a lot to the development of fluid dynamics. Stokes considered the fluid flow in creeping flows. Creeping flow occur when the viscous forces tend to dominate as compared to momentum forces. So in the equations of motion, the momentum forces can be ignored as compared to the viscous forces, and therefore the motion in such a case will be very slow. As you can see that, for example, the fluids which have less viscosity like air, like even you may consider water, the fluid, if we throw it away, if we let the fluid flow, you will see that the velocities are pretty fast. But if we consider the flow of oil, the flow of, let's say, honey, then you will observe that the motions are relatively slow. So creeping flow occurs in such cases when the fluid in question is something like honey or oil or anything that has a higher level of coefficient of viscosity or kinematic viscosity. Here is a similar problem under consideration. We consider a fluid flow which passes past a sphere. So it will be something like that. If there is a sphere and the flow is flowing, then how does it look like and how the fluid behavior occurs when the fluid is passing past a sphere, as we can see in the picture. Now we try to consider a similar solution in which we have to try and see how the forces act and how the forces behave. So again, this is a difficult problem, and to solve it, it was a brilliant thinking of Stokes and other mathematicians who developed this methodology. And what they did was that they first tried to non-dimensionalize the equations. And as you know, we non-dimensionalize the equations by considering the basic things, that is the dimension of length, the dimension of time, and similarly the dimension that occur as far as the equations of motion are considered. So we take for time, we write it as t asterisk or t star equals to ut over L. And you know the dimensions of velocity u is distance over time. So length is a distance, time is a distance, and if we divide u by length over time, it will be a non-dimensional number. And if we write it in the way that we have written here, you can see that this reflects time. So we write time, t star, in a non-dimensional form as shown here. Similarly, x star, the length, as x over L. So x is the length, and if it is divided by some standard length L, it will become a number. And similarly, the pressure forces. So all the terms that are shown here with star are non-dimensional terms, and the terms that are without any superscript or suffix, they are dimensional. And from these terms, we define a number what we call as Reynolds number. Reynolds number is defined as the ratio of a typical velocity of a fluid flow problem into length divided by kinematic viscosity nu. You will see that the dimension of this are 0, and so this is a Reynolds number is a dimensionless number, and it shows the ratio of momentum forces and kinematic forces. And so P infinity is the pressure at infinity. So when we substitute in the equations of motion to dimensionalize it, we obtain the equations in the form that we have shown here. Divergence of u is equal to 0. So there is nothing, no number occurring now, that is no other factor multiplying. But when it comes to the momentum equation, the momentum components of the equation of Navier-Stokes, then when we non-dimensionalize all the terms by substituting the length and the time as we mentioned, then the terms on the left are multiplied by Reynolds number, and all the terms on the right hand side are non-dimensional. So we assume that if non-dimensionalized form u is equal to 0, the velocity on the surface is 0, and we can see it because if we are assuming that this viscosity is high, so the fluid will be tend to stick to the surface of sphere, for example, in this case, because of the viscous effects, because of the viscosity. And the velocity u over u, as x tends to 0, this will act in this form, in some number. So, and then the Reynolds number is this quantity which we have mentioned many times, and we have described also here as inertial forces and viscous forces. So the Reynolds number is far less than 1. Then the left hand side, since it is multiplied by this, it will become a small quantity as compared to the quantities that occur on the right hand side, and therefore we can ignore them, and the equation will only be reduced to minus gradient of P plus del square u. And then rewriting these equation in the dimensional form, the equation will be reduced to these two equations, and then the set of these equations are known as the Stokes equation, because he first of all derived them. And if we write down if we replace u by vorticity terms omega, the equation will reduce to these equations, and the pressure term will be del square P. By substituting the equations, as you know, that u is equal to dc d psi by dy, and v is equal to minus d psi over dx, the equations of motion can be reduced to d4 psi equal to 0, where we take d square to be this term, and we can verify it. And obviously, when I was talking about the stream function, I had mentioned this equation.